depending on what type of how hot it is, how, you know, pretty much, yeah, how hot it is, how much energy are we talking, nuclear reaction will require a certain level of that within the star. So it's not like maintaining nuclear reactions endlessly is very possible. Even within the very extreme environments of a star, it could actually run out of nuclear power, especially after it makes iron. Iron, as I was mentioning, is a very stable nucleus. It'll start to basically make an iron core. So where everything is just making more and more iron, and iron is very stable. So to go from iron to the heavier elements require a different kind of process, which may or may not happen. And if gravity wins at any point in all of this, then literally the star is too heavy and it's not doing enough nuclear reactions, so it cannot keep going, and it collapses upon itself, collapses upon its own gravitation. So that's literally the core collapse supernova, and apparently those are the more common ones, according to this. Type 2 supernovae slightly more common than type 1a. So this is an expanding nebula around the nova GK Persei. This is a nova example and an expanding nebula. So after a nova happens, or pop quiz, I did a pop quiz. Yeah, it's kind of like a firework. So expanding nebula around the nova GK Persei. Basically, that's what we get, right? When there's a nova, there's this expanding material around it. Even the supernova ultimately will have this expanding material, which is, we call those like a nebula, gas cloud, whatever. And ultimately, it can make planets like us. So it's really very interesting and exciting. Oh, thank you. I love your comments. Keep on going, Kimmy. I love it. I love all the comments, especially the related ones, related to the live ones. So it's really, really nice of you. Very helpful. Thank you. I'm super supportive of your channel. Thanks. Universe is a giant expanding nova. No. So the universe is not... Universe, remember, we talked about cosmic inventory. The universe is much more than a nova or a supernova. Remember, so this is all a star exploding, ejecting material, ejecting neutrinos, ejecting photons, neutrinos, and these elements. Iron is just the ordinary material is just baryons. Remember how we talked about the universe's sure, it's a bit like the Big Bang, but the universe is more than this. So this is just an event in the universe. The universe is more than this. So that's where I want to be clear. A supernova, a nova, is an astrophysical event, astronomical event, astrophysical event, whatever. Involves astrophysics. The universe is more than that. The universe is cosmology, which is a bigger picture study of the universe and its evolution, its beginning, its changes, where the universe is now, etc., etc. And the biggest thing that's missing from this discussion is dark energy and dark matter. Remember, we don't know what dark energy is and we don't know what dark matter is. Nowhere in this nova and supernova discussion did we have to talk about dark matter and dark energy. Whereas when we talk about the universe, we do have to talk about those things. So the universe's expansion is not to do with this. the universe's expansion has to do with dark energy, and we don't understand what that is, and we are researching that. Well, we don't even know about dark matter and dark energy, so there are questions to be answered about the current universe, and whether that's from its beginning to now, or now and then beginning. What came before the universe is another question. It is another question, but I would say there are questions about the universe that we are in at the moment that we cannot yet fully answer. No, is this why you were? No. So the investigation for neutrinos is to study astrophysics. I did not specialize in dark matter, but I'm interested in dark matter as a topic. But the study that I was doing, looking for neutrinos, those neutrinos are extragalactic astrophysical neutrinos, potentially from these various astrophysical events, like what we're talking about here. So this is the distinction I want to make. What we're talking about here is astrophysics. This is like when we talk about a single star or a few stars or a galaxy, our galaxy is still very local compared to the entire universe. When we talk about a star dying, a supernova, a nova, those are astrophysical events. So when we talk about getting extragalactic neutrinos, the extragalactic neutrinos coming from specific sources or astrophysical events would tell us about those astrophysical events. They might help us with some question about the universe, but the question of dark energy and dark matter are more broad than that. Those are more of a cosmology question. Do you see what I'm saying? I was not trying to study dark matter and dark energy. Now, it is true that neutrinos were a considered candidate for dark matter, but at this point we think that neutrinos are not, in fact, what mostly would account for dark matter, because neutrinos are too low mass. So, neutrinos are interesting for multiple reasons, right? I'm saying mainly what the motivation was. Mainly, when you study particle astrophysics with neutrinos, you're basically saying that you're going to use neutrinos as the particle for studying a certain astrophysical event, or maybe many astrophysical events, like if you just caught all of the neutrinos that came from extragalactic sources, it would be like, that's novel in itself, right? Because generally we see other signatures of those types of events. So it's a way of doing astrophysics with another particle, with another method other than light and whatever else. It's like, it falls under multi-messenger astronomy. Because like something like an astrophysical event is very, very small compared to the entire universe. The universe, how it began, how it evolved, the cosmic ingredients, that's a much more, that's a cosmology thing. That's a broader topic or a different topic. It's, all of it is interesting, but neutrinos as they relate to, say, the Big Bang, if I could find like Big Bang neutrinos, that would be cool too, actually. Shit. I should look that up. I should look that up if anybody has. They're not going to be as high energy though. So I should also note that another reason for using neutrinos for these astrophysical events is because Yeah, I'll answer that. The another reason for using neutrinos for this, remember we were trying, so it's a very specific topic. Particle astrophysics, the way the stuff I was doing, is a very specific topic. It's also about very high energy events and these natural particle accelerators, sites in the sky, maybe extragalactic, probably extragalactic, which are naturally accelerating particles to a very high energy. So when you probe those events, you're learning specifics about those events. And when you say you've caught, say, a neutrino from those events, then that's another way to look at those events. It's a probe into that particular astrophysics. So it's an astrophysics thing. Cosmology has to do with, yeah, the universe. Now, what's more interesting to me? I think when I was in grad school, astrophysics was more interesting to me. But now, since I pretty much all of it is, I gotta look at it. So now I might be more interested in cosmology at this point. I think I wanna learn more about dark matter and dark energy. Just because that's more of what I didn't do in the past. So yeah, it's all of it is interesting. It's different. But if you can't conclude the origin, oh yeah, let me see if I'm gonna make a short YouTube video with adoring comments of your channel. Oh, thank you. Thank you, Kimmy. Appreciate it. Yeah, tag me. I'll comment on it. Thank you, everybody. Can we get 20 likes, please? But if you can't conclude the origin of the high energy particles, I don't understand what you could learn. We can conclude the origin of the high energy particles. So we can do directional astronomy, right? Like neutrinos don't interact with most things and they're not charged, so they don't get deflected by like magnetic fields in the galaxy and things like that. So neutrinos are actually the rare kind of particle that do point back to their source. So that is actually one of the motivations for using neutrinos to do particle astrophysics. Whereas photons can get attenuated, cosmic rays can get deflected, gravitational waves are kind of hard to detect. You would need bigger, more cataclysmic events to be sensitive to gravitational waves. Neutrinos are also hard to detect, but when you do detect them, they generally point back to their source. So if you do directional constraints, then you should be able to say where they came from. Like your search would have to include direction as a constraint, not just time. Yes, and by optically, you probably mean by any light. Yeah, basically you could get neutrinos potentially from a gamma ray burst, and you would know, hopefully you got the gamma rays or whatever other wavelengths of light too from that source. And there are a lot of detectors for gamma ray bursts, constantly, looking for, surveying for, and detecting gamma ray bursts. So then say you're also ready with your neutrino detector. You don't even have to know in real time that you were looking for a gamma ray burst neutrino. What you would actually do is a blind search for a neutrino, and you would constrain the search in direction and time to line up with the gamma ray bursts. And then see if you can find a neutrino when the gamma ray bursts happen and in the direction in which the gamma ray burst happens, so that you could definitively say whether the neutrino came from the gamma ray burst or not. Stuff like that. It would be better to have these high energy sensors in outer space at distances apart to be able to sort of triangle. So putting things on outer space always costs more money. So even though we do put stuff on satellites and things like that, but it really depends on the funding that this topic would be getting, which I'm not sure that I don't know if high energy. Actually, they talked about putting a, I don't know what happened with that, but they talked about putting a neutrino detector on the moon at one point. So I would say for neutrino stuff, the bigger issue is generally the fact that there's a lot of noise that you have to deal with in the data. So it's not so much that we don't have a lot of diversity of directions, because remember how gamma ray bursts are very far away. So it's not like we don't see a lot, right? Like from all kinds of directions, and they're isotropic in direction, actually. Like we get gamma ray burst signals coming from all sorts of directions in the sky. It's not like if we were in space, you know, sure, that could be something, but on Earth too, we get them. Oh, and actually, what am I even saying? So certain gamma ray burst detectors are actually in space. So, but neutrino detectors, I don't know too many, I guess, I don't know any neutrino detectors in space. Maybe there are such things, but I know that there are gamma ray burst detectors in space. So then the question is that really what the people suffer from is anthropogenic noise is a big deal here on Earth. So because the neutrino signal can, well, anthropogenic signals can sometimes look like the neutrino signal, more than likely that's the issue, and not the fact that we would need to be in space because of the direction stuff. But I mean, who doesn't like to be in space? So if somebody wanted to build a neutrino detector, the other thing too is that you need neutrinos that are high energy neutrinos, and in general neutrinos don't interact with much. High energy neutrinos will interact more than lower energy neutrinos, but basically because they don't interact a lot, you would basically need a ton of instrumented volume of some material in order to detect them. So this is kind of hard to put in space, right? I mean, what is in space which would readily interact with neutrinos a lot? And then for us to catch it, right? we want the interaction to happen and the signature of it to be caught. And so we use Antarctica and all of its ice as such a thing. We've even thought of the moon as being such a thing. But in space, you have to ask the question, what exactly is your detection method? If that makes sense. Okay. So that's sort of the that's the neutrino stuff. It's very, well, neutrinos also are an important cosmic inventory or cosmic ingredient, or it's part of the cosmic inventory. So the cosmic inventory is, again, photons, baryons, neutrinos, dark matter, and dark energy. We know three of these things. We know photons, that's light. Neutrinos, we talked about neutrinos, it's a weakly interacting particle. And we know what baryons are. Baryons is what make up us, protons and neutrons. Elements, that's baryons. But those are a minority, turns out, in the cosmic ingredient, and most of the cosmic ingredient is actually dark energy and dark matter in this current era of the universe, which, by the way, the universe has evolved a lot since its beginning. So at this point, if you were to catch a neutrino that's from the Big Bang era, like a primordial neutrino, that could be really cool. I don't know if people do that yet. And so neutrinos have always been part of our story. So in general, the particle neutrino is interesting. If you get neutrinos from specific interesting sources and events like these supernovae things that we're talking about, or whatever else, then that's interesting for probing those particular events. But for cosmology, we need to be thinking more large scale and thinking how, say, for example, dark matter affects distribution of galaxies in the universe, or how dark energy expands our universe and why it's even happening. Those are the questions. And those are sort of very fundamental questions, but they're also kind of different from generally. There's overlap between cosmology and astrophysics, but it's not the same. And that's why sometimes I take time to actually describe what these things are, what the topics are. They're not the same thing. Do you have any ideas on what dark energy is or why the universe is expanding? No, I'm really stumped, actually. I really don't know. Yeah. Actually, fun fact, I was studying dark energy at one point in grad school. I was in a couple of cosmology groups. Because of totally, stupid reasons, human reasons, like funding and all that stuff, and politics with professors, I did not continue my cosmology route and went towards a particle astrophysics route and got my PhD in particle astrophysics. Well, it's always in physics, but the subtopic was particle astrophysics. But I did do cosmology for like a year or so, a year or more. So I did rotations in cosmology. You know what I mean? So thank you. Yeah, so I did have some opportunity to study the topic, but right now, for example, the dark energy survey, the dark energy spectroscopic instrument, like there are big collaborative work happening in that area. And it will be very interesting what they come up with. And they do need a lot of good people. So I'm hoping that the science outreach here kind of educates more and more people, and more people can join the efforts. But thank you for the faith you have in me. I'm just a mere human, one person. My job there was something quite different. I can't say too much about it. Something like that. So yeah, the pure science stuff is nice because you can educate the public on it. And I do hope that the channel helps with more and more pure science outreach, and people get to learn these topics and realize that there's an abundance of such topics to be learned and researched still. Indeed, there are many, many things we don't understand, and these require a lot of effort and a lot of research. And, hopefully the funding is there, and hopefully more and more students can join these efforts, because believe you me, there is much that we don't know and don't understand, dark energy and dark matter being two such huge examples of that. And hopefully this is motivating people to learn more about it and research more about it. And some of the experiments and collaborations that are in these fields are very, very big. But there's still always a lack of good people to work on things. Because many of the people are involved in administering the efforts, maybe not so much in doing the efforts. So maybe you can do the efforts, children. Maybe I can also do the efforts. Oh, that's not true. I think people are actually very smart. I think people are really smart, but they might not have had the right exposures to things and whatnot. And also, I think a lot of smart people don't really go into academia. There are smart people working on more real world problems and industry problems and things like that that they focus on. And so there's not the manpower or the woman power to or the them power to work on dark energy and dark matter. Apparently not anyways, because we still don't know what those things are. Hope that helps. Did you ask me something about why I don't like men? That's because many of them are criminals. Just kidding. Actually, not really kidding. But I do like supportive people. Is it shooting shit time? Yeah, sure. Let's do it. Hi, Caddy Sever. Please rewind. Please rewind the live to see more material on Nova and Supernova. And please like the live. Can you please like the live? Can we get 20 likes? Last night I got 40 likes. Somehow today we only have 16 likes. It's shooting the shit time. I think I'm gonna do galaxies tomorrow. I'm tired. That gym class wore me out. Hello. Hi, Ketty. I got 120 followers on my Facebook thing today. Today? Did you post something? Oh gosh. It's so cold. Oh, your business page. Congratulations. It is so cold here. It's 2 degrees Fahrenheit, and so I think I'm feeling more. Oh, and I also swam a lot. That's why I think I'm more cold and sleepy. That's why I'm more cold and sleepy. But thank you everybody so much for joining, and do rewind to see more about the nova supernova. Sorry, there were some distractions in the beginning and my output I think was a little intermittent, but eventually it stabilized. Thank you, Ketty. I don't quite understand what you're saying, but thank you so much for being here. Reese says thank you, of course. Somebody might need to translate for me whatever Ketty is saying. Thank you. Can we get 2 more likes and get 20 likes? Yeah, I try not to get distracted, but today my mind was a little bit here and there. It's a little here and there. Can we get 20 likes? I think we did. Thank you so much. Thank you. My face always looks weird on these lives because it's like reversed, you know? Like my face is actually the other way. It's like a reverse face that I'm seeing. But whatever. Who cares? Who cares? Ooh, so tomorrow I think we're going to talk about our galaxy. In fact, I'll give you a preview now because I'm feeling happy. I just remembered something. Our study of stars began with the definition of the word star. A sense of symmetry compels us to begin our study of galaxies with the definition of the word galaxy. So we did not define galaxy yet, I don't think. So let's have a definition. A galaxy is a collection of stars between 1 million and 1 trillion of them in round numbers plus gas, dust, and dark matter held together by gravity. A galaxy is bigger than a star cluster, such as Pleiades, Pleiades, however you say that, and smaller than a cluster of galaxies, such as the Virgo cluster. So Virgo cluster is a cluster. It's a cluster of galaxies, a group of galaxies. Although there are hundreds of billions of galaxies within the volume accessible to our telescopes, we will start. So there are hundreds of billions of galaxies within the volume accessible to our telescopes. We will start by looking in depth at the galaxy in which we live, which is the Milky Way galaxy. So tomorrow we will take a closer look at the Milky Way galaxy. Oh, I have a picture to show you. I have an awesome picture to show you. What's funny? Nothing is funny. I'm just feeling happy about something. I just remembered something and I felt happy. That's all. Let me show you a picture now. Look at that. Look at that. That's the Milky Way galaxy, our own galaxy, seen from Mount Graham, Arizona. If you go to Arizona, make sure to look up. Look at that. How amazing looking. Oh! Disc shape. On a dark night far from city lights, you can see a luminous band of light across the sky. Yes, we are a spiral galaxy. Yes, but we see the band because we don't see the full you know what I mean? So we see a luminous band of light across the sky, forming a great circle on the celestial sphere. So like, here's the sky. The Milky Way is like a band across the sky. The rest of the sky is not the Milky Way. Those are other things. We can see a lot of galaxies. When we look up, most things we see are actually a galaxy. I don't know. I don't know. I don't know about that. So when we look up, say you go to Hawaii or a remote dark place or this Arizona spot, when you say you lay down and you look up, you see all of the sky, right? The Milky Way is just a band across the sky. Because of our own position in the Milky Way, we have a certain view of it. And that's the band across the sky. Look for that band across the sky. Okay. Everything else, those are mostly other galaxies that we are seeing. Yay! Can we get 30 likes? So, in English, your language, this band of light is called the Milky Way, because it looks to the naked eye like a luminous white fluid. In ancient Greece, it was called the Galacticos Kuklos. Galacticos Kuklos. Galaktikos space Kuklos. Kuklos, which translates literally as Milky Circle. Milky Circle, because it's a great circle within that celestial sphere. If the celestial sphere is what we're looking up at, the Milky Way being sort of a band across the sky is a great circle on it. So, Milky Circle, from 40 astronomical units away, apparent. Oh, okay, you're talking about Voyager. The Greek word galacticos is the origin of the English word galaxy. So Milky Way is one name of it. And then where does the word galaxy comes from? It comes from this Greek word. Greek word galacticos. Although the Milky Way looks as if someone spilled glow-in-the-dark milk across the celestial sphere, when Galileo examined it with his telescope, he found that it is actually composed of a very large number of stars, each individually very faint. Very faint indeed. A hypothesis that explains the existence of the Milky Way is that the sun is embedded in a relatively thin disk of stars. When we look perpendicular to the disk, we see few stars and the sky is dark. When we look in the plane of the disk, we see the many stars that make up the Milky Way. This disk of stars is a major component of the galaxy in which we live, which is therefore called the Milky Way galaxy. It is also called just the galaxy. Or if we're feeling particularly possessive, we can call it our galaxy. So if we say our galaxy, Milky Way galaxy, that is the galaxy we are in. It's our home galaxy. And when we look in the plane of that disk, we see many, many stars. The first method used to determine the size and shape of our galaxy was the method of star counts. To demonstrate how star counts work, let's start with some simplifying assumptions. All stars have the same absolute magnitude, M, big M. This is not true in general, but we can choose to look only at main sequence stars of a particular spectral type. So stars spend a lot of time, by the way, on the main sequence. Our sun is on the main sequence. So you could say, okay, let's look for main sequence stars of a particular spectral type. Let's see where that gets us. The number density of stars n is constant within our galaxy. That's an assumption as well. Here, things got kind of faint and dark. I don't know why. Maybe my phone is being weird. Okay, I'm just making sure. There is no absorption due to dust. Now that too is not true, but it's an assumption, a dubious one. A star of absolute magnitude big M will have an apparent magnitude small m. So I think, yeah, that m we were talking about earlier, I think it was apparent magnitude. It wasn't too it wasn't super important, but that I think that's what it was. Anyway, this absolute magnitude m will have an apparent when it's at a distance d, then your apparent magnitude comes from the big M as 10 to the 0.2 times m minus m plus 5, and all of that is in parsecs. So this is a conversion to get the apparent magnitude. Every star closer than a distance d will be brighter than this small m. So as you get closer, it will be brighter. Makes sense? That's the total number of stars brighter than m will be some more math. By going one magnitude fainter, you should, so as you get fainter in the magnitude, you should increase the number of stars you see in a given patch of sky by a factor of 10 to the 0.6, which is around 4. It's math again. So basically, as you go one magnitude fainter, you should increase the number of stars that you are seeing in a given patch of sky by 4, because you've gone farther. If the galaxy were infinitely large, which it is not, then as we counted stars as a function of their apparent magnitude, we would find that log n just kept increasing to arbitrarily large values of small m. So yes, more math, more things. And remember, we had some assumptions here that are not quite correct, but gives us an idea. Gives us some idea. What happened to shooting the shit? This is more math. 36 likes. Can we get 40 likes? Can we? 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 Get 40 likes? So did you know that the pioneers in using star counts is a pair of brother and sister? The lurkers are liking. Yes, please. Welcome, welcome. Like the live. Thank ya. The pioneers in using star counts to determine the shape of our galaxy were William and Carolyn Herschel. William and Carolyn Herschel were siblings, and we call this the Great Sibling Act of Astronomy. I'm here like 5 minutes, and this already has way too much math. Hi, Panda. How do you do as well? Welcome to the live. I think you'll find the rest of this mathless. So William and Carolyn Herschel did this star counting stuff with all that math we talked about. Your live stream is showing up in shorts recommendations. Well, thank you so much. Welcome, welcome. Look at that. Welcome. Welcome, welcome. So in the late 18th century, they did star counts in various regions of the sky. You can just choose a patch of sky and do it. And came to the conclusion, this brother and sister pair, that our galaxy is shaped like a grindstone. If you don't know what that is, a grindstone is a thick disc made of coarse abrasive stone. Unfortunately, the Herschels were unaware of the existence of interstellar dust. So they assumed no dust, no absorption by dust, and did not take into account extinction by dust. As a result, they came to the erroneous conclusion that we are near the center of a relatively small galaxy. We're not near the center. We're off to the side. The notch in the grindstone is actually the result of a dust lane down the center of the Milky Way. So they thought that it was a grindstone-looking thing like this. We are talking about our galaxy. Welcome to the live shorts viewers. If you were thinking of relaxing as you scroll shorts, hello, welcome. Come on in. A more accurate determination of our place in the Milky Way galaxy was provided by Harlow Shapley in the early 20th century. Oh yes, and can you please like the live? Shapley did it by looking away from the dust-laden Milky Way and examining the distribution of globular clusters. Can you please like the live? Do you watch sports? I do not. Hi, Fawcett. How are you? We will not talk about globular clusters. What team do you support? Do I have to support a team now? I don't really watch sports. Oh, for Jamaican cricket? Damn, you have a nice voice. Oh, thank you. Well, come on in and like the live. A globular cluster is a compact cluster of stars containing as many as 10 to the 6 stars within a spherical region 30 parsecs in diameter. So, when we look at globular clusters, we see an absence of hot main sequence stars. Why do you radiate so much good energy? It is because I'm a spiritual being. Speaking of globular clusters at the moment. Thank you so much for being here. Can we get 40 likes, please? Thank you. So did you know that typical ages estimate globular clusters to be about 12 gigayears? 12 billion years old only. Ooh, maybe I'm from a globular cluster and I am 12 billion years old. Some people ask me my age on the live here sometimes. Our galaxy has about 150 globular clusters associated with it. So we're not very young, guys. The nearest globular cluster is M4, which is about 2 kiloparsecs away from us. The most distant of our galaxy's globular clusters is 100 kiloparsecs away from us. Can you like the live, shorts viewers? Shapley noted that the globular clusters are not uniformly distributed across the sky. Aha! Thank you for liking the live. Shapley, wow, okay. Shapley did something. Instead, they're concentrated in one half of the celestial sphere, centered on the constellation Sagittarius. Now remember, Sagittarius we've talked about. Is it the same Sagittarius? Did you know that when you click your fingers, the sound comes from the finger striking your palm? I don't think I know that. Well, maybe. Can we get 40 likes? So they're concentrated, these globular clusters are concentrated around the Sagittarius constellation. So, oh. Are you a tarot reader? Are you asking if I'm a tarot reader? Maybe I should start reading tarot. Maybe. Ooh, can you subscribe? Can you like, share, and subscribe? So globular clusters are all orbiting the center of our galaxy. So by the way, here it comes. Reese, what is at the center of our galaxy? We know. Can you use my name in a sentence? Facet M. Facet M? Yes! There is a supermassive black hole at the center of our galaxy. Rudolph the red-nosed reindeer. Sometimes I sing. Brings people in. Can you please like the live? Thank you so much. So globular clusters are all orbiting. I love the science she's teaching. Thank you. Thank you for liking. Thank you for subscribing. Thank you for sharing. It's 2:27 in the morning. I'm loving that you're all here. So the globular clusters are all orbiting the center of our galaxy, which lies in the direction of Sagittarius. Thank you. Hi, Meherana. Thank you for liking. In addition, he measured the distances to globular clusters using RR Lyrae variable stars, standard candles. It's a method in astronomy. Nearly 50! Yes, 50 likes, please. Thank you. But it turns out that the distances were too large. But he had the right order of magnitude. Can we get 50 likes? Hi, Mehrana. Are you from Iran? Welcome to Iran. So this discovery that we're not... So modern distance measurements tell us that the distance to the galactic center is around 26,000 light years, which is around 8 kiloparsecs, 8 plus or minus 1 kiloparsecs. That's where we are from the galactic center. Thank you, Kimmy. And this discovery that we're not at the center of our galaxy, like we're not geocentric, and guess what? In our galaxy, we're not towards the center now. And good, because at the center, there could be some issues. So the fact that we're not at the center of our galaxy has been called an extension of the Copernican revolution, because remember, Copernicus is the one who suggested heliocentric model. And this is sort of adding to that. Copernicus said that the Earth is not at the center of the solar system. Shapley said that the solar system is not at the center of the galaxy. And before you ask, the galaxy is not at the center of the universe. In fact, as far as we know, as far as we can tell, the universe doesn't have a center. Aww. Do spiral galaxies always? Many galaxies do have a supermassive black hole at the center. Yes. Many galaxies are known to have that. So, great. We have discovered that we're not at the center of our galaxy. We're around 8 plus or minus 1 kiloparsecs away from the center. We're off to the center. We're off from the center. We're off to the side, not the center. We're not at the center. We're off to the side. Around 8 plus or minus 1 kiloparsecs away from the center. Okay, which is around 26,000 light years, and the entire galaxy from one end to the other is around 100,000 light years across, okay? So, the universe is complicated. As far as we can tell, we know not of a center of the universe. Thank you. Can we get 50 likes? Ooh, next we will talk about population 1 and population 2 stars. So the universe started from a singularity, the Big Bang, and it started from a singularity. And it has expanded because of dark energy, but we know not of a center of it, okay? The universe is a bit more complicated than normal. Because Reese, remember that the universe could be, for all I know, the universe operates with more dimensions. We experience 4 dimensions, but it could have more, okay? Can you say uwu? What does that mean? Ayad Al-Ahmad. Hello, Ayad. What does that uwu mean? Bay says Mehrana. Never mind. Okay. Can we get 50 likes? Sort of. Okay, so our galaxy has a few parts. One part is called do you speak foreign languages? I speak English, Bengali, Hindi, and Urdu. Will that do? So our galaxy has a luminous component. The most luminous component of our galaxy is the disk. We kind of mentioned the disk already, so we'll come back to it, but that's one thing, disk. Then we have a second component of our galaxy, which is called the bulge. If you look at the Milky Way at infrared wavelengths to minimize the effects of dust, you see a bulge in the direction of Sagittarius near the galactic center. The central bulge of our galaxy is about 1 kiloparsecs in radius, so you can see it stick out above and below the disk. At the very center of the bulge, there is a tiny nucleus bright at radio wavelengths. We talked about that. It's the supernova or supermassive black hole. What am I saying? Supermassive black hole, which eats material from nearby objects and accretes, and that makes the radio wavelengths happen. Yes, so we talked about the disk. We have a disk in the galaxy. We have a bulge. The third component of our galaxy is the halo. Not like Halo Moto, but halo. H-A-L-O. Halo. The halo is a roughly spherical distribution of stars, about 100 kiloparsecs in radius. Thus, it extends far beyond the disk. The halo has the same luminosity as the bulge, but its stars are spread over a volume about 10 to the 6 times larger. The three stellar components of our galaxy, disk, bulge, and halo, differ in their stellar populations, as well as in their size, shape, and kinematic properties. So we will talk about stellar populations. Not all stars are from the same population. Not all stars belong to the same generation. So let's talk about that. The thin disk contains relatively young stars for the most part and is where most star formation is occurring today. Thin disk stars tend to be rich in metals, with a mass fraction in metals of Z over 0.01. In the jargon of astronomers, stars that are young and metal rich are called population 1 stars. Can we get 50 likes? By contrast, the halo contains stars that are relatively old and low in metals. So these are called metal poor stars, by the way. And these are population 2 stars. It's almost like a backwards way of naming them. So metal poor stars are older stars, but they're called population 2. You know, the thick disk contains stars that are intermediate in their properties between population 1 and population 2. Thus, it is described as having an intermediate population of stars. And the bulge contains a mixture of old and young stars. So it is a place where population 1 and population 2 coexist. Here is an artist's impression of the spiral arms in our galaxy along with its central bar. Here you go. We actually have looked at this picture before. In fact, my phone is dying, so yeah. We will, there's a few pictures. Let me show you. Let me show you. Let me plug in the phone and show you more pictures. Indeed, pictures are going to be upon us now. Where's my whey protein container? I put the phone on top of that and I show you the picture. Can we get 50 likes? Here you go. You can even see Sagittarius A. Yes, so right here, this is the Sagittarius arm. This is the galactic bar. This is the long, so galactic bar right here, long bar. There's another bar right there. This is the near 3 kiloparsec arm. This is where we are. See how the galactic center is over here? This is where we are. See, little sun right there. That's where we are. This is the Orion spur. This is the Norma arm. There's some arms, let's just say. Lots of arms. But very interesting that we're not at the center, right? Thank you for liking the live. Really appreciate you guys. So this is called Scutum Centaurus arm, Norma arm, galactic bar, Sagittarius arm, far 3 kiloparsec arm, near 3 kiloparsec arm. All we know is, you know, big radio source here because Sagittarius star, which is the actual supermassive black hole, is constantly eating material from its surroundings. So those falling accreting material will give us big signals in radio waves and other wavelengths. This is where we are. This is our galaxy. This is where we are. That's the center. This is where we are, not at the center. This is the Orion spur, Perseus arm, outer arm. So this is so lots of arms here, right? One arm, another arm, another arm, another arm, another arm, another. So lots of arms. Outer arm, Scutum Centaurus arm, Norma arm, near 3 kiloparsec arm, Sagittarius arm right here, Sagittarius arm, us, Perseus arm, outer arm. No, we're not older because we're part of that thin disk we mentioned. We're part of the thin disk. So this said, the stars that are young and metal rich are called population 1 stars. The thin disk contains relatively young stars. So the sun is a young star. It's not a very old star. Nope. See? Thin disk right here. That's where we are. Sun. Oh yeah. Oh yeah, this is upside down. But, upside down as in, you mean the text? Yeah, it's upside down. Okay, galactic center, us. Hopefully that helps. Thank you, everybody, for being here. Let me know any questions. This is called scutum Centaurus arm. The sun is located in a short stub of a spiral arm, usually called the Orion spur. Right here. Orion spur. Nestled inside the Perseus arm. This arm. The Orion Nebula, the local hotbed of star formation, is situated within the Orion spur. So Orion Nebula is going to be making new stars and things like that. And hi, Fuji. So we have a pretty star formation rich neighbor in the Orion spur. Pretty close to us. But, you know, pretty close is still pretty far in astronomy. Hi, Sachi. Turn your phone around, Kimmy. Yes, please. Thank you. Do that. Sorry. Can we get 50 likes? Hi, Sachi. It's so cold here. Ooh, if you want, we can look at another thing. Turn your frown upside down again. Are you going to watch Contact one of these days or what? Oh, thank you. I will. This is NGC 891 with a D of 9.8 megaparsecs shown in the large binocular telescope first light image. Ooh, if you could view the Milky Way galaxy from outside, oriented so that the disk were edge on, it would probably look like the galaxy NGC 891. Notice the prominent dust lane running down the middle of the galaxy. It is generally true for disk-dominated galaxies like the Milky Way and NGC 891 that the dust and gas is confined to a much thinner disk than the stars. So here's another galaxy for you, sort of what our galaxy would look like if we saw it edge on NGC 891. Large Binocular Telescope. Pretty, right? This is NGC, another one kind of like us. Can you centralize the picture at all? Yes, this is an image. Yeah. We can't take an image of the Milky Way because we're in it. But yeah, this is an image. As in, if we went outside of the galaxy, then we could, but you know, that would be pretty far. So Milky Way, we're in it ourselves, no image, but we can image other galaxies. Indeed. No, this is NGC 891. How can we take a picture of the Milky Way edge on? We're in that galaxy. We're in Milky Way. We can't take a picture of the Milky Way edge on because we're in it. We can't readily go outside of the Milky Way. It's very far. But we can image other galaxies edge on or whatever on. And this is an example of such a galaxy that we imaged edge on. It's called NGC 891. Good picture showing. Sometimes with teaching, it can seem like reading a storybook to kids. But it's normal and understandable why. Can we get 50 likes? Obviously, we can't photograph. Exactly. NGC 891. Good night. Me too. I gotta go too. I need to go to bed. Thank you. I do need to go to bed as well. Thank you so much. Oh my God. I'm a little tired. I'm a little tired. Good night, Kimmy. Thank you for being here, Kimmy. Always good to have you. Thank you so much. Pinned your comment. Thank you. Bye-bye, everybody. Thank you for being here and modding, Reese. Oh, okay. Thank you. Fuji? shoes look chilly. They want snacks. I love you.